Today we're going to talk about doing inferences for means. We've done inferences for proportions, both one proportion and two proportions, where we're comparing the two proportions. This is the first chapter in the next section.
Oh,
Okay, so this will not be on our next test, which I think must be next week.
I think it is, yeah.
I think it's next Tuesday.
And we're off Monday,
Yeah,
so we'll have to review before then.
I believe that that's the case. Let me double check. Ah, yes. So the quiz is not Friday.
Oh,
The quiz is Thursday.
Thursday.
And then on Friday, we'll go over the quiz and go over the review and take the test on Tuesday, which isn't optimal, but
No,
I couldn't figure out a better way to make it work.
that works just fine because we have all day Monday to study. So
Yeah,
we're off Monday.
if you use it.
Oh, we will.
Sometimes when you have a lot of extra time off,
Yes.
you're like, oh, I have all this extra time. And then at the end, you're like, I did less than I would have done if I didn't think I had much time.
Happens to me all the time.
So, all right. So, a reminder of the central limit theorem. So, if you draw a random sample from any population, it doesn't matter if it's skewed, bimodal, whatever, with a mean of mu and a standard deviation of sigma, its sample mean, y bar, has a sampling distribution with the same mean, but whose standard deviation is sigma over the square root of n, where n is the number in your sample. So, and we write sigma of y bar, or standard deviation of y bar, is equal to the standard deviation of the population over the square root of n, which is the size of our sample. We've done that before. That's not anything really new. No matter what population the random sample comes from, the shape of the standard deviation, take two. So no matter what the population the random sample comes from, the shape of the sampling distribution is approximately normal as long as the sample size is large enough. The larger the sample used, the more closely the normal approximates the sampling distribution for the mean. I don't think I can say that whole sentence at once. Right? So here we have some problems, though. So at this point, we realize that if we're trying to estimate the mean of a population from a sample, is if we don't know the mean of the population, then we probably don't know the standard deviation of the population either. And if we don't know the standard deviation of the population, we can't find the standard deviation for the sampling distribution. You're like, oh, well, what are we going to do? So the workaround for that is to use the standard error, just like we did with proportions. To do this, we'll estimate that the standard deviation of the population is the standard deviation of the sample. So what we're actually going to do is, when we're finding the standard error for y bar, we're going to take the standard deviation of our sample divided by the square root of n, because that's all we're going to be able to do. It turns out that this really does work pretty well with the normal model as long as the sample size is large enough. The problem comes in as the size of the sample gets small. The normal model does a poorer and poorer job of what it's supposed to do, which is to tell us about our population. So the sample distribution will still be unimodal and symmetric, but it becomes less normal as the sample size decreased. So how did we get around this problem? Well, it turns out that a really smart guy by the name of William Gossett, who was the chief experimental brewer for the Guinness Brewery in Dublin. Yep, the people who make Guinness Stout, and then the other variations. He was doing experiments, but the problem was he was doing experiments on trying to make their beer better, right? And the problem was is that it was way too expensive to do this on a whole lot, to do a very large sample size. So he had smaller samples and he realized they weren't very normal. So what he came up with is something where the distribution, it's not normal, it is unimodal and it is symmetric, but it's not normal. And it depends on a parameter called the degrees of freedom. We'll talk a little bit more about that. The degrees of freedom of a distribution represent the number of independent quantities that remain after we've estimated the parameters. And you're like, and it's okay if your eyes kind of gloss over when we're talking about the degrees of freedom. These are called students T, or simply T models. Now, you may be wondering, where did this students T come from? Well, the Guinness Brewery Company had a pretty good, for their sake, clause in his employment that said he couldn't publish anything that he discovered while he was working for them, because they were very secretive. Even though this was just a statistical thing that he discovered. And so it got published as the students model. But it was really William Gossett who did it. So in our case, we're trying to estimate the population mean from a sample, and the degrees of freedom is going to be n-1. However many are in your sample, -1 tells you the degrees of freedom. So, what are the conditions for using a student's T model? Well, they're kind of the same as they have been, but not quite. So you still have to have the randomization condition. So if we're looking for a random sample or a suitably randomized experiment, that's what we want. If it's not true, but we believe the sample is representative of some populations, you need to limit your conclusions accordingly. You need to say something about that. The independence condition, we're sampling without replacement, which is almost always what you're doing when you're taking a sample. The selections are not technically independent. To prevent that from becoming a problem, we impose that 10% condition. Notice that if you're doing an experiment, you just want to say somewhere in there, it's like that it's reasonable to assume that each individual we're using in our experiment has results that are independent from one another, that they don't depend on each other. And then the nearly normal condition, so the data come from a sample that appears to be unimodal and symmetric, without strong skewness or potential outliers. So part of this is, did you take a big enough sample to make it no longer skewed or no longer bimodal? Right? Remember when we looked at this before, if you had something that was bimodal and you took a big enough sample, the sample starts looking unimodal, right? The sample means when you take the sample over and over and over again. So you want to have a sample that looks that way. How do we check that? You can do it with a histogram. You can do it with a box plot. I don't like those as well. I think it's harder to see skew on those. You can also look at something called the normal probability plot, which should be basically straight. If it's not basically straight, then your original graph or your original data is not going to look very normal. So once these conditions have been met, the standardized sample mean, T, which is going to be y bar minus mu. Remember, y bar is going to be the mean of our sample mu is going to be what we think the mean is. That over the standard error of y bar, it follows a student's t model with n minus 1 degrees of freedom, where the standard error is the standard deviation of the sample over the square root of n. All right, turn the page. Let's take a look at how is this different than a normal model. So that one in black is your standard normal model. Okay, and that's based on a z-score. So if you look at the one at the very bottom in the middle, that's a student's t, or just a t-score with only 1 degree of freedom. Notice a couple of things. See how it's a lot shorter in the middle? But then to make up for that, it's a lot taller on the ends. The tails are fatter. And I have seen questions about that on the AP exam, where it'll ask you something about, well, what's going to be different? Well, one of the things is the tails are fatter. But notice that as the degrees of freedom go up, the student's t model begins to look more and more like the normal model. It gets closer to that. Now, one of the other things that happens is with the normal model, in between -2 and +2, we collect an awful lot of data, right? What's the percentage for 2 standard deviations to either side? Is it 95%?
Yes.
So we get 95% of our data in between those two. Notice with the student's t, we don't. Because like here, where it's only got 1 degree of freedom, there's a lot less area underneath the curve than there is underneath the standard normal model. Okay?
Mm-hmm.
So let me see if I said all the things I was supposed to. Note that the t distribution is shorter in the center and taller on the ends. So it has fatter tails. This means that for a t distribution, we must go more standard deviations from the mean to capture the same area as is under the normal distribution. So note also that the t distribution becomes pretty normal as the degrees of freedom increase. So let's take a look at this one, and we'll save page 3 for tomorrow. A bakery owner purchases bags of powdered sugar from a new food wholesaler. Because the wholesaler is new, the owner wants to make sure that the bags are properly filled on average. Here are the weights in grams of 10 randomly selected bags of powdered sugar from the wholesaler. And we have all these different ones. Create a 95% confidence interval for the mean weight, mu, of all the bags of powdered sugar sold by the wholesaler. Based on this, should the owner be convinced that the bags are being filled with less than the 907 gram average purported by the wholesaler. So the wholesaler says, my bags have an average of 907. We're going to look at a confidence interval to decide, is that true or is that not true? All right, so let's pull this up.
Mr. Davis, the screen's not on.
Oh, I didn't realize the screen wasn't on.
Yeah, I was wondering if you knew if it was on or not.
No.
Because we were just reading, so I figured you'd be waiting for it on.
All right, so here we're looking at one mean, and on the NumWorks calculator, it says, notice that it's a t-test or a z-test. If you're looking at the TI, you don't have that problem.
This is on distributions?
This is on inference.
Oh, inference and then a one mean, and then t-test or z-test.
Yeah.
Which one is
Hang on just a second, let me get this going. So on the TI, it's just a t-test. And actually, we want a t-interval. That's somewhere on here. Yeah. On the TI, you can choose between summary data or the statistics. So here, since we actually have the statistic, we have the data as opposed to the summary. I said that backwards a second ago. We have the raw data as opposed to the statistics from that. It's easier just to leave it in data and tell it all these things. But before I do that, I need to go to L1. So I'm going to quit out of this. And then I'm going to enter all of this data. So 910, 919, 900, 913. Brody, while I'm doing this, you can be looking at, can I do the same thing on the numworks or not?
Yeah, I was thinking, trying to figure that out. Because I'm on tests, right? Once you go to or no, we're looking for an interval because it's 95% confidence interval.
Yep.
Okay. And then T interval. Input statistics.
I think that's all of them.
Yeah, now I'm stuck.
So now I'm going to go back to test. And it's a T interval. And did they say 95%? Yeah. And it's 900.92 to 912.68. So 900.92 to, what was it? 912.68. And we'll always write down the other things that they give us. So the average was 906.8. And we don't need to, so this is our standard error, is the 8.2165, blah, 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 blah. And we could get that by taking the 906.8 minus the 907 over, there were 10, and we're taking the square root of that. Let me remember. Oh, sorry. The square root in the denominator, not in the numerator. Oh, that's where we get T. Yeah. Anyway. So we've got our T interval there. On the numworks, we're doing a t-test. And I want to do an interval. I need to tell it that first. And it's one mean. We're going to do a t-interval. So look, you can either input the statistics or you can use a data set. So that just means we have to kind of do the same thing we did on the TI. We need to back out of this and input a data set. Oops. Back up on statistics. So we're going to enter all those. And I'm going to move this out of the way.
Oh, they have to be in order.
The order's not important at all.
Okay.
So now I go back to my inference. And we're going to use the data set. One of the nice things is that when you go back to the inference, it picks up where you left off. And we actually could have done it from here. You don't actually have to back out, which is a slight advantage it has over the TI. Confidence level 95%. And it gives you the mean is 906.8, which is exactly what we found before. The sample standard deviation is 8.2165. Sample size is 10. It gives you the t critical value. We don't typically bother with that. And the standard error and the degrees of freedom, which notice is 1 minus or 1 less than the number we had in our set. And it gives you the confidence interval, which is exactly what we had on the other one. So based on this, should the owner be convinced that the bags are being filled with less than 907 gram average?
No.
No. Why?
Because 907 is included in the confidence interval.
Yeah. Because 907 is within the confidence interval. All right, we'll leave the rest for tomorrow.